Video, we're going to start talking about how to find x-intercepts of the quadratic functions that are perfect square trinomials. And before we start working with the factoring process, we first want to talk about what are perfect square trinomials. And generally, remember when we're factoring trinomials, we're going to have two factors and each factor with a binomial in the expression. And this is essentially the structure we're going to expect in this particular section as well, except these trinomials are going to work out nicely as perfect squares. And because we said the trinomials will be factored out to be two factors of binomial expressions, we're going to expect the same over here. So generally we are going to say that for it to be a perfect square trinomials, the factored result either looks like the form of some expression a plus some expression b squared, or it could look like some expression of a minus some expression of b squared over here. And in order to find out what it looks like in the FOILed out form, we can kind of think back to this idea of how we would calculate a plus b squared. And remember, when we have a plus b squared, it's really the same as a plus b times a plus b. Using the FOIL process, we're going to distribute the first over here. So a times a gives us a squared plus the outside. So the outside is a times b plus ab. And then plus the inside over here. So the inside is positive b times a, and we know for multiplication the order doesn't matter, it has a commutative property, so we can write it as ab again. And last we have b times b, which is plus b squared over here. Now looking back to the form after the FOIL process, we would have a squared plus 2 times ab plus b squared. And that's essentially what we should expect in a trinomial form before we start the factoring process. And whenever we have a form that resembles a squared plus 2ab plus b squared for some expression a and b, we can eventually factor this out to be a plus b squared. And you can do the same process for a minus b squared. And in order to do this, we would have, again, a minus b times a minus b, because that's what squared power means. Now using the FOIL process, first a times a gives us a squared again, and then we have outside, so a times negative b, which would be negative a times b, and then we have inside negative b times a. For the same argument as before, we can switch the order of a and b these expressions, and that becomes negative ab again. And last, negative b times negative b becomes positive b squared. Again, combining the like terms, we're going to have a result of a squared minus 2ab plus b squared. So anytime we have the form of a trinomial that resembles a squared minus 2ab plus b squared, we know this is going to be a perfect square trinomial, and that can be factored out to be a minus b completely squared. And notice the only difference between the two is if you had addition between the terms in the factored form, you should expect this linear term in our trinomial before factoring to have a plus sign as well. And similarly, if you had a minus sign in the factored form, what you started with should also have a minus sign to connect the linear terms. And that's what we're going to look at over here and see how each example would resemble that form and how to recognize the whole idea of perfect square trinomial. And if you look at the perfect square trinomial form, we're going to kind of thinking about working the process backwards, because our given problem is always going to be in the trinomial form. So these are the results that we found out. And we want to work our way back to make sure that we actually do have that a and b form that satisfy the FOIL form. So for example, if we look at part A, the first thing you want to recognize for any perfect square trinomial is that the first term and the last term need to be perfect square terms. So for example, if we had the first term being x squared, we know this is x times x over here. And based on our form that we want to look for, that means we can assume that our a is equal to x, because if we want the first term to be a squared, that means that a in this case is equal to x. And now on the other hand, for the last term is a linear term that should look like b squared over here. And now for 9, this is where it's helpful to know your perfect square numbers. We know 9 is equal to 3 squared. So if 3 squared equals b squared, that means b equals 3. And that's a connection we want to make first in order to check whether something is a perfect square trinomial. Now if I can see that a equals x, so a squared is x squared, which matches our first term, and b equals 3, so b squared equals 9, which is our last term. And then in the middle, I have this plus 6x. And ideally, I want this 6x over here to be 2ab. And if that's the case, we can say that we have a perfect square trinomial. So we really want to check whether 2ab is equal to 6x over here. And now if we plug the information we have, we know a is equal to x, so I'm keeping the 2. A is equal to x, b is equal to 3, and we want to check whether that's equal to 6x. Here, if we multiply everything on the left, we have 2 times 3, which is 6, so we indeed have 6x equal to 6x over here. That means if I have this checked out, this is a perfect square trinomial. In particular, this is a perfect square trinomial that will become a plus b squared, because I have a plus sign in front of the b term. And therefore, we can say f of x is equal to a plus b squared, which is equal to x plus 3 squared, because a is equal to x and b is equal to 3 in this case. Now if we want to look at a different problem where we have the function in b, the first thing you want to notice again is the first term over here, x squared, is a perfect square. That tells me if I want to match it with a perfect square trinomial as a result, I need the first term to be a squared. So a has to be equal to x. And now similarly, if we look at b, we know 16 is equal to 4 squared over here. And notice we're only working with a positive square root in this case, because the signs will automatically be taken care of when we look at the term in front of the linear term over here, or the coefficient in front of the linear term here. And then we can say that b, therefore, is equal to 4. Now I want to check whether 2ab is equal to our 8x over here. And a is equal to x, b is equal to 4, and we want to see whether that's equal to 8x. So multiplying everything out, we do get 8x is equal to 8x over here. And then we get g of x is equal to, in this case, a minus b squared. And remember, it's a minus over here because we had a minus over here in front of the linear term, the middle term. And then we can say a we said was x minus b we said was 4 squared. And that's going to be the factored form. And I noticed a question was asking what are the x-intercepts, and I forgot to answer that question. So we're going to finish this part B and go back to part A to answer that question as well. So in order for it to be x-intercept, we again want g of x to be 0, so that means x minus 4 is equal to 0, or x minus 4 squared is equal to 0, based on the zero product principle. And therefore, x equals 4. And our x-intercept is going to be 4, 0. And whenever we have a perfect square trinomial, we can expect to only have one x-intercept, because what happens is that the vertex actually falls exactly at the turning point. And that's what essentially makes it a perfect square trinomial, because there's only one single x-intercept without any additional values that would create a 0 for the function. Now moving back to part A, since I forgot to answer the question about the x-intercept, we again can set x plus 3 to be equal to 0 and x equals negative 3. So our x-intercept here is going to be negative 3, comma 0. Again, whenever we have a perfect square trinomial, we should only have one x-intercept. That also will become our vertex. If you actually check the vertex formula, you will get the same thing. And it's not quite a coincidence when you think about the vertex formula being x equals negative b over 2a, which is essentially the first part of our quadratic formula. And these pieces all connect together, and therefore, if you check your vertex formula, you're going to get the x-coordinate of the x-intercept for the perfect square trinomial. Now, with this in mind, let's move on to parts C and D over here. In part C, again, we have this plus in the middle, so I know that eventually I want to check whether that's equal to a plus b squared. And now if we look at the first term, we have 4x squared. And when we have 4x squared, if we want to write it to be something squared, we can say this is equal to 2x, because we're essentially taking the square root of 4 and taking the square root of x, both. So square root of 4 becomes 2, and square root of x becomes x over here. And if you want to double check your work, just square the entire of 2x, you should get 4x squared. And our b is a little more straightforward. We have 1, and 1 is this magical number we have in factoring process that's really helpful. 1 can really be written as 1 squared over here. So our b is equal to 1. And this is going to be a nice perfect square number we have. Now we want to check whether 2ab is equal to our middle term, which is 8x. So here we would have 2 times 2x being a times b being 1. And in this case, if we want to find out whether this works, I just want to check whether this equation is true. And if we actually check, you'll notice this is not true. But for the sake of our practice, I'm going to change this problem. I believe this was a typo, and this should really be a plus 4x. And when we have this case, we would have 4x over here, and we want to make sure whether this is equal to 4x. If you had the problem that was 8x in the middle, you would say this cannot be factored as a perfect square trinomial, but because for this video we're focusing on the perfect square trinomials, just to demonstrate the point and practice more with this form, we're going to change the problem and make sure it works out nicely. It doesn't always work out if you have just randomly given trinomials, and that was an example. You can see that's why it's important for us to always check that our trinomials work. So here we get 4x is equal to 4x, this checks, and therefore our h of x is equal to a plus b squared, which becomes 2x plus 1 squared. Now using this result, we can find the x-intercept by setting this only factor 2x plus 1 to be 0, and x will be equal to negative 1/2 as a result. So for the x-intercept, we have negative 1/2, comma 0. And that's going to be the only x-intercept or vertex. And now for the last part, we can do the same thing. We want to again check for the first term, it's a perfect square because 9 is a perfect square, x squared is a perfect square. So using this, we know a equals 3x. And the last term, 4, it's a perfect square because 4 is 2 squared, and b is equal to 2. And based on this, we can find out whether 2ab is equal to the middle term. And our middle term here is the 12x. Again, I'm not going to worry too much about the minus sign because the minus sign will be addressed in the final form, whether it becomes a plus b or a minus b. That will be addressed based on that. and we have 2 times ax, which is 3x, times b, which is 2. And if we multiply this out, we want to check whether this is equal to 12x, and if we do so, we would have 12x equals 12x over here. So this checks, and that means this is a perfect square trinomial, and j of x therefore will become a minus b squared. Again, we have a minus here because we had a minus in the middle term, and therefore we would get a being 3x minus b, which is 2 squared. To find the x-intercept, we can go ahead and set this to be equal to 0. Therefore, 3x equals 2 and x equals 2/3. So for the x-intercept, we are going to state it as 2/3, comma 0. And that's how we can find the perfect square trinomial x-intercepts. And as we said, for any time you have a perfect square trinomial, you should always expect to have only one x-intercept, and that will actually coincide with the vertex of our quadratic function, or our parabola in this case.